last three parts, what we have seen is using Bernoulli equation for calculating flow rate given a power, or for a given flow rate how much power I would require. So what we will do now is we will try to look at some things related to measurement of flow rate. Okay? And then we'll talk about a little bit about two-phase flow, and when you have not just a single phase but flow of gas and liquid flowing through the pipeline. Okay, okay, so here this is where we are on Bernoulli's equation, and flows through pipes and fittings. We have seen pressure drops in pipes and fittings and piping systems. This is where we are. Just to quickly let you revise, how do we define equivalent diameter for non-circular pipes? Why do fittings cause head loss? Now question is not how much, I'm asking you why do fittings cause head loss. Think about that. Why do different fittings cause different head loss? So if I say a bend versus, let's say, a gate valve, why do they cause different head loss? Name the different types of valves used in industry. You can go back, read the video, see the video, and answer that yourself. Which type of valve causes large head loss? How is the head loss due to valves and fittings calculated, and more importantly accounted for the total frictional head loss in the piping? So answer these questions. That will help you to revise the previous part, and then you can see this or you can understand this part in a better manner. So we have been talking about Bernoulli equation, and now we are going to use Bernoulli equation for measurement of flow rate. We'll see how that works. So one of the things that we use is something called as an orifice meter or a venturi meter. So imagine that this is a pipeline and this is an orifice that is there in the pipeline. So this is an orifice plate. Orifice plate, we have seen in the last video, is just like a plate with a hole inside, so that the whole flow goes through this hole, right? And the streamlines become like this, and these vortices are formed here, and that rotating packets of fluid, vortices, these cause pressure drop. Okay, and what we measure is the pressure difference between somewhere here and just downstream of the orifice. That's called as a differential pressure across the orifice. Now if you look at the center line and plot different variables, say for example, first of all we plot velocity. Okay, as we go from here to here, so this is say somewhere here. Okay, let's say velocity in this is the velocity of the pipe. Now as we go along, cross-sectional area is reducing because here only this much area is available for flow. So as the velocity reduces, as the cross-sectional area reduces, what happens to velocity? Velocity will go up. And if velocity goes up, by Bernoulli equation, pressure will reduce. Now beyond this point, velocity is increasing. Beyond this point, cross-sectional area is increasing, velocity will reduce. And if velocity reduces, pressure increases once again. But this increase in pressure is not as much as what it was earlier. So this pressure now is something lower than what we had at the upstream, and this pressure is called as permanent pressure drop. Permanent. That is permanently lost. That pressure head or that pressure energy is permanently lost. That's why it is called as a permanent pressure drop. Whereas this pressure drop is called as a differential pressure drop. It is there what is across the orifice. Now if I take point 1 and point 2, I can apply Bernoulli equation. Now this Bernoulli equation we are writing slightly differently in terms of per unit mass of that substance. We have divided by we have divided throughout by rho. Okay, so that's why this HF is capital HF divided by capital HF multiplied by rho. So this is per unit mass. So this is slightly different, but just a different way of writing. Ultimately, it doesn't matter. You can start with that equation as well, and you can get this. So now, if you talk about Bernoulli equation between 1 and 2, H1 and H2 is the same. So they will just cancel out. W is not there. W is 0. There is no pump between 1 and 2. Right now, let us neglect this HF. Okay, so if I rearrange this equation now, P1 minus P2, that's what I measure. This is P1 and this is P2. This is what we measure, pressure differential. So P1 minus P2 by rho would be V2 square minus V1 square by 2. And now V1 and V2 I can relate by material balance. So if let's say D1 is the diameter here and D2 is the diameter at this location, diameter of the orifice, then I can relate this by material balance. D1 square V1, that's the volumetric flow rate, multiplied by pi by 4 of course, and pi by 4 just cancels out from both sides, is must be equal to D2 square and V2. So V1 I can replace as D2 square divided by D1 square minus multiplied D2 square divided by D1 square multiplied by V2, and then V1 square would be square of that. V1 square would be V2 square multiplied by D2 by D1 raised to 4. Now this ratio D2 by D1 is the ratio of diameter of the orifice to diameter of the pipe. We are going to call that by a symbol beta, just the area ratio. So delta P, I can write this in terms of beta raised to 4. Delta P by rho would be V2 square by 2 multiplied by 1 minus beta raised to 4. Now I can rearrange this to give you V2, velocity through the orifice. So velocity through the orifice would be 1 minus square root beta raised to 4 into square root 2 delta P by rho. So if I measure delta P by a manometer or a differential pressure measurement device, we have seen that in the class in the third lecture, I can calculate V2, velocity through the orifice, and once I know velocity through the orifice, multiply that by pi by 4 D2 square, I can calculate flow rate. So I can get to know the flow rate through the pipeline by measuring this pressure differential, and you have an experiment which will allow you to measure this P1 and P2, and you will be able to calculate measure the flow rate and then calculate something more. Now, so this equation accounts for no head loss, no friction because of these vortices. HF we have neglected in getting this equation. But if HF is actually there because of these vortices, then the actual velocity will be a lot more pressure drop. So the actual velocity for the measured pressure drop will be less, and we use this equation by accounting for that head loss, but we account it for by some constant. This constant we call as discharge coefficient for the orifice. Discharge coefficient. Last class we have seen discharge coefficient of valves or valve coefficient CV. They are same. That formula and this formula is the same. Only thing is that formula was in terms of flow rate. So if you had multiplied by area, if you had multiplied by flow rate on the left side, you would have got the flow rate. You could have written this in terms of flow rate being proportional to square root delta P by rho, and that proportionality constant is our discharge coefficient of valve or the valve coefficient CV. Open the last lecture and see this for yourself. It is one and the same. Okay, that's how measuring delta P across the valve, and if you know the valve coefficient, we can calculate the flow rate through the valve. Same way here, knowing the discharge coefficient of orifice, oh, sorry, spelling mistake, coefficient CI, oh, let's rub coefficient, CIET. Discharge coefficient. Okay, so this is how we can measure flow rate using an orifice meter. Now, this permanent pressure drop is can be very large. So one couple of things we need to discuss. First of all, suppose beta is something like 0.3, 0.2. Then this root 1 minus beta raised to 4 can be almost equal to 1. So sometimes we can even neglect this, and in typically in valves we neglect that because beta is very small. Now, if I the next point is, because there is a frictional loss because of these vortices, this discharge coefficient is always less than 1. It can never be more than 1. It is less than 1. Typical values of discharge coefficient, typical value of C0 is around 0.6 for an orifice. So these vortices or these rotating vortices, this is what causes the pressure drop, and this is what causes permanent pressure drop. This permanent pressure drop. So therefore, using an orifice causes a loss, permanent loss in the pipeline. If I have not used, this P1 and P2 would be nearly equal. P2 will still be less, but it will be very slightly less because the pipe size, because it's only this much amount of straight pipe. But because of orifice, because of these vortices, there is a large pressure drop, and the permanent pressure drop, if beta is small, permanent pressure drop can be as large as the differential pressure drop, which means this blue line would be like this. There is practically no recovery of pressure. This is called as a pressure recovery zone, where pressure increases because velocity is reducing, because cross-sectional area is increasing in this direction. That's called as a pressure recovery. So pressure recovery practically does not happen for orifice if beta is very small. So the permanent pressure drop can be as large as differential pressure drop, maybe 90% of that, maybe 80% of that, right? Depends on the beta value. And therefore this orifices can also be used as something called as restriction orifice. You saw that in the last lecture, but I did not spend time there. Now we can spend time. They can be used to reduce the flow in a pipeline by deliberately causing pressure drop. So sometimes we have a pump which is of a large size, but then we don't want that much to flow to go through. We would like to cut down that flow. So one way of doing that is putting a orifice called as a restriction orifice, permanently reducing the pressure, increasing the pressure drop, and therefore reducing the flow. But that causes that's an energy loss, power loss. And remember that even a 5 kW power per year is equivalent to few lakhs of rupees per year. So these permanent pressure drops are to be avoided. And the way we can avoid that is if we prevent these vortices from forming. So instead of making an orifice, we will make the pipe like this. We will make the pipe like this, and we call that as venturi. So a venturi meter will look something like this, and orifice meter will look something like this. So orifice meter looks something like this. This is what we have seen, permanent pressure drop. And a venturi meter, we make the profile itself like this, so that these vortices that form here, they do not form, and then the pressure can recover, velocity will come back to its original value. Velocity comes back here automatic always. There is no difference in the velocity here and here, no difference in the velocity here and here. That's based on material balance, steady state. But pressure can recover now as much as the actual value. So the permanent pressure drop will be practically negligible, and if permanent pressure drop is negligible, it is equivalent to saying, or these vortices are negligible, it is equivalent to saying that this HF is practically zero. So this formula should be almost valid for a venturi, and it is almost valid. So we use a formula called, instead of discharge coefficient C0, we put a CV, venturi coefficient, and then that CV is almost equal to 1. So typical values of CV are 0.98, 0.99 and so on. Okay, so we can use orifice meter or we can use Venturi meter for measurement of pressure drop, and then measuring the pressure drop we can relate it to the flow rate through the discharge coefficient of orifice or discharge coefficient of Venturi. So that's how we use orifice and Venturi for measuring the flow rates. Something else to measure the local flow velocity. So imagine that there is a pipe. I told you about velocity profile. So velocity is smaller here, larger here, larger here, larger here, larger here. Okay. So if I put a tube like this and connect this to manometer, let's connect it to manometer. Right, let's connect this to manometer. Let's just put a red pen. Yeah, let's just put a manometer here. Let's say this side is open to atmosphere and connect this to manometer here, and we take some manometric fluid. This is a manometric fluid. Now I can apply Bernoulli equation. So water will be here, water will be present all throughout this pipe. Okay, and this is a manometric liquid. Let me just put some other color. Let's put this brown. So manometric fluid is here, could be mercury, and it is open to atmosphere on the other side, or it can be even be connected to here. This limb you can connect to here. This limb can be connected to here, depending on what this pressure is. Now if I apply Bernoulli equation between 1 and 2, okay, no pump, frictional head loss is negligible, H1 and H2 are the same, I can relate, and V1 and V2. So remember V2, the fluid comes here and stagnates. It doesn't go through here. So velocity here is 0. Velocity at location 2 just inside the tube is 0. It's not going here. So velocity at 2 is 0. So to that extent, the pressure on this second P2 will be higher than P1 by an amount equal to V1 square by 2G. Here is the so this is negligible, this is not there, this is not there, V2 is 0. So P2 will be larger than P1 by an amount equal to this. So P1 is called as a static pressure. We can even call this as a dynamic pressure. Of course, we have to multiply by rho, then they have units of pressure. So V1 now I can calculate from P2 minus P1 by rho, or V1 would be square root 2 delta P by rho. Very similar to what we had here. Okay. Now I can take this tube up and down, and the pressure difference that I register, I will get local values of velocity. So this pitot tube is used to measure local values of velocity. Especially in civil engineering, we use weirs. Okay, so what is a weir? Imagine that there is a river, or imagine that there is a channel which is taking water from here to here, from left to right in this direction. We put an obstruction, then the water level rises and the water flows over this weir. So this black plate, vertical plate that we put inside the flow is called as a weir. This is our weir. Now flow will go over the weir. Now I can apply Bernoulli equation between 1 and 2, right? Both are open to atmosphere, so P1 and P2 will cancel out. No pump, no friction, very little friction. H1 minus H2 is now small h, this height. V1 is negligible, so V1 is like the free surface of that channel which is carrying water. V2 is larger because now whole of water has to go through this cross section area. Okay. So then I can get V2 in terms of H1 minus H2 or H. H1 minus H2 is nothing but H. Now I can take a differential element like this. Flow rate through this differential element would be V2 multiplied by area of this cross-sectional area. Velocity is in this direction. Cross-sectional area is perpendicular to this velocity. So that's dh. Dh, if you like, is the height of that differential element multiplied by w, that is the width in the direction perpendicular to the screen. So w into dh is the area, differential area of this element multiplied by velocity, and I have to integrate that from 0 to h, and then you will find that the flow rate is given by this formula. Derive it for yourself. So civil engineers or environmental engineers, when they want to measure the flow rates in large streams, say wastewater um, or storm water flows or river flows, so you can put a weir in that and measure the height. So whenever, let's say, bridge is being built, it partly blocks the cross section of the river. Let's say we are trying to build a bridge on a river, so the pillars of that bridge block partly the flow of that river, and same thing happens, that the flow happens over that weir or over that blocked portion. And then measuring the height of this portion, height of this overflow, we can measure we can calculate the flow rate using this formula. We don't use it often because our pipelines are not open, they are closed, so we use more of venturi meter and orifice meter. Just one small point is the orifice meter and venturi meter, they measure this differential pressure or a differential head. So these are called as variable head meters. Okay? Head is varying depending on the flow, and it is head that we measure. So these are called as variable head meters. Right? Okay. V notch again. So imagine that flow is coming towards you through this plane, or going into this plane, or going into the screen perpendicular to the screen. So flow is in this direction. Flow is either coming towards you or flow is going perpendicular to the screen, inside or outside. So then we can block a part and have a notch in that, and then the liquid level will rise in that up to a certain value, let's say this value, capital H. Again, we can apply Bernoulli equation between point 1 here and point 2 here. We will still see that V2 is square root 2 GH. Now the area is only different. Area is the area of cross section of this differential element. We can relate that to the angle phi and capital H. So you can calculate that, and then you can derive this formula yourself. This is for a V notch. Again, civil engineers, when they want to use open channel flows, they use this very often. We don't use it that often. We don't use it much. Other types of flow meters are something called as turbine meter, ultrasonic flow meter, magnetic flow meter, vortex flow meter, Coriolis flow meter. What we will do is we will see a small video, and then all these different types of flow meters, they will become very clear to you. Okay, and you can see these videos again later on as well, whenever you wish to see. Okay, so here are the videos. Here are the videos. So flow meters differential one. The differential flow meter is the most common device for measuring fluid flow through pipes. Flow rates and pressure differential of fluids such as gases, vapors, and liquids are explored using the orifice plate flow meter. The differential flow meter, whether Venturi tube, flow nozzle, or orifice plate style, is an inline instrument that is installed between two pipe flanges. So this is a pipe, and we are going to put this orifice. You see, this part is blocked. This is only an opening, and it is connected. It is put between these two. These pipes are closed, and then these flanges, bolts are connected.
The orifice plate of the flow meter is comprised of a circular metal disc with a specific hole diameter that reduces the fluid flow in the pipe. Pressure taps are added on each side of the orifice plate to measure the pressure differential. According to the laws of conservation of energy, the fluid entering the pipe must equal.
So the whole pipe, liquid is flowing in whole pipe. Now it has to come through this small region, orifice. So the streamlines bend and then it goes up. So you can see now area available for flow is reduced here and area available for flow is increased here. So velocity is reducing, pressure is trying to recover
The mass leaving the pipe during the same period of time. The velocity of the fluid leaving the orifice is greater than the velocity of the fluid entering the orifice. Applying Bernoulli's principle, the increased fluid velocity results in a decrease in pressure. As the fluid flow rate increases through the pipe, back pressure on the incoming side increases due to the restriction of flow created by the orifice plate. The pressure of the fluid at the downstream side of the orifice plate is less than the incoming side due to the accelerated flow. With a known differential pressure and velocity of the fluid, the volumetric flow rate can be determined. The flow rate, Q, of a fluid through an orifice plate in.
So they are using this expression Q is equal to K delta P, but we use in terms of velocity and the orifice discharge coefficient. In valves, this is what is typically done. But is there any formula you can use? We know it is coming from Bernoulli equation and flow is proportional to delta P.
Increases in proportion to the square root of the pressure difference on each side multiplied by the K factor.
So K is a constant for that particular orifice.
For example, if the differential pressure increases by 14 psi with a K factor of 1, the flow rate is increased by 3.74.
Square root 14. So another video. Here you can see these vortices. In this video you will be able to see these vortices nicely. Again, it's my company Anderson Hauser. This is just one of the instrumentation companies. There are several such companies. Only the video is nice. I am not advocating a particular company here. Let's fast forward this little bit. Their introduction is little too long. So we'll start with from here. Let's start from here.
Therefore, different principles for their measurement are required. One method is flow measurement, based on the differential pressure principle. Some 300 years ago, Swiss mathematician and physicist Daniel Bernoulli discovered the direct relationship between the pressure and speed of a fluid flowing in a pipe. Italian physicist Giovanni Battista Venturi also performed experiments on flow, and in 1797 he built the first flow meter for closed pipes, known as the Venturi tube. Here is how this measurement method works. Differential pressure flow meters have an artificial restriction integrated into the measuring tube, illustrated here by the example of an orifice plate.
This is an orifice plate.
Two holes are located in the pipe wall, one before and one after the orifice plate. Two separate tubes connect these holes to a differential pressure sensor with its two pressure chambers separated by a diaphragm. The tiniest pressure differences in the flowing fluid can be precisely measured. If the fluid is not flowing, the pressure before and after the orifice plate is essentially identical. As soon as the fluid starts to flow, its velocity around the orifice plate increases significantly because of the restriction in the cross-section. At the same time, due to the laws of fluid mechanics, the static pressure at this point decreases. Consequently, different values are detected in the pressure chambers of the sensor. A higher pressure before and a lower pressure after the orifice plate. This pressure difference is a direct measure for the flow velocity, and thus the mass and volume flow in the pipe. The higher the flow velocity, and the resulting drop in pressure around the orifice plate, the greater the differential pressure measured. In numerous industrial applications, the orifice plate covers many needs of flow measurement technology. However, other designs are available for certain measuring tasks to minimize undesired effects, such as excessive pressure loss or abrasion of components due to solids carried in the fluid. This demonstration shows that an abrupt restriction generates severe turbulence in a fluid. Nozzles with a rounded...
See, now these, just let's go a little back. Yeah, you see these rotating packets of fluid, vortices. That causes
turbulence in a fluid.
Permanent loss.
Nozzles with a rounded, funnel-like inlet clearly reduce turbulence and thus create less pressure loss. Nozzles are particularly suitable to higher flow velocities or to fluids with abrasive solid particles. Turbulence reduction is even greater with Venturi nozzles. And finally with Venturi tubes, where the restriction is created by longer conical constrictions in the pipe wall. All these designs can be supplied with different restriction diameter sizes, so that the pressure loss and the differential pressure generated can be optimized for the process conditions. Industrial flow measurement using differential pressure has been tried and tested in numerous applications worldwide for about 100 years. With this measuring principle, all liquids, gases, or steam can be measured, even at extremely high process pressures and temperatures. Every differential pressure flow meter manufactured by Endress and Hauser is configured to customer specifications and pre-mounted.
Yeah, so don't worry about that. I mean, all instrument manufacturers will do that for you. There's nothing special about this company. Let's look at one more video, the different types of flow meters.
There are many types of flow meters available for use in industrial automation. Depending on the product to be measured, whether it's liquid or gas, some basic principles apply to how the meters work. If you enjoy these video-based or conductive, this makes the measure. Let's take a magnetic flow meter, or mag meter. The measured liquid must be water-based or conductive. This makes the mag meter a great choice for wastewater or processed water that is considered fouled or dirty. Mag meters are volumetric meters that have no moving parts. This is ideal for those areas where you wouldn't want to be exposed to the measured liquid while working on the meter. The way a mag meter works is based on a formula called Faraday's formula. Firstly, again, the liquid must be conductive. A voltage is measured that is dependent on the average velocity of liquid, times the strength of the magnetic field, times the length of the conductor. This is the distance between the electrodes. This is all that wonderful science stuff. Theory of relativity. However, the people both benefit. We don't need necessarily even whomever invented the measured work based on Faraday's formula. Other flow meters work in different ways. For instance, a mechanical flow meter has some moving internal parts which may not fit with specific applications, such as dirty water that carries large...
Like a turbine, right? So flow is there and turbine is rotating. And therefore this kind of meter has a rotating part, and therefore you don't want it to have dirty, or you don't want it to have solids. They can accumulate and foul, and because of moving parts it requires more maintenance as well.
Particles that may cause damage or obstruct the internal parts. The mechanical flow meter has a rotational device inside, such as a paddle wheel or a propeller. Liquid flowing through a pipe causes the rotation of the internal paddle, which creates a flow rate that is proportional to the rotational speed of the internal paddle. The mechanical flow meter is easier for layman correlation road. Principal turn sends a graduated. That's the simplified version, but there are other takes care of for you. I'll go into a formula that will correlate. There are other types of flow meters. There's vortex, which measures vortices. Essentially, a sensor tab will bend and flex from side to side as the vortex passes.
See, now this is a pipeline, this is a vortex flow meter. There is a device which is deliberately introduced, so the flow has to go around this and vortices are generated. Let me just show you. Imagine that we had that ball. Imagine that we had that ball. This is not this one. No, not this one. I can't remember which one. Let's see. Let's see this. No, not this one. This is okay. We can see this. Yeah, this one. Okay. So imagine this is a pipeline, and we have put this inside that vortex flow meter. So when flow goes around, you see these vortices that are generated. You see these vortices that are generated. You will be able to see this more clearly in this simulation. This is simulation, right? So this is something that we put in. Oops. Yeah, so this is something that we put in. Flow is going from left to right, and these vortices are generated. So if I have let's just take one more. This one I'm just not finding. Yeah. So you can see, suppose I put this inside in that vortex flow meter, and flow is going from left to right. These vortices form, and these vortices go along for so long. Now if I put something here, something in this flow, it will alternately get hit by this vortex, this vortex, this vortex, and so on and so forth. So the flap, if I put here, it will just flap depending on, it will just vibrate depending on when these vortices pass. And we measure the frequency of that flapping, and we would be able to calculate the flow rate going through this we were somewhere here. Yeah, so this flap is flapping.
Bend and flex action will then produce an output frequency that is proportional to volumetric flow.
We'll see why that in a later.
There are also ultrasonic flow meters. The principle behind these meters is that an ultrasonic signal is transmitted downstream or in the direction of the flow, while another signal is transmitted upstream. The delta, or differential time, is used to calculate the velocity of the liquid.
So this is calculated based on the Doppler shift. Remember, the Doppler shift is proportional to the velocity, and therefore there must be some particles which will be able to scatter the ultrasound.
That velocity is then used to calculate the volumetric flow through the pipe. As you can see, There are many types of flow meters for various applications.
So there are many types of flow meters for different applications, and then this as you practice and go into plants more and more, you will be able to figure out more and which type to select when. So let's go forward in our course. Okay, something that we need to do very quickly. In fact, this presentation or this video will be there. You can see this in lot more detail. I will cover little very briefly. Suppose we are having two-phase flow. So we have a flow of gas and a liquid in a pipeline. So these two phases, when they flow in different ways. Either you can have a stratified flow. So the red is gas, so gas going, and a liquid flowing below, stratified flow. It can be wavy stratified. It can be elongated bubbly flow, slug flow, annular flow. Now means gas is outside and liquid is inside. Or you can have a dispersed bubble flow, means liquid is throughout and gas is in the form of bubbles. So different flow regimes are possible when you have two phases flowing in a pipeline. What we will do quickly is these are the different flow regimes possible. They are given in terms of a regime map, and this regime map is available for different kinds of fluids. When you do an experiment, you will be able to see for yourself the different types of regimes that are possible. What we will do is we will just try to calculate. I'll give you one method of calculating pressure drop when there are two phases flowing, gas and liquid. Why this is important is, imagine that there is a tank here and liquid is flowing here. When two phases are flowing, when liquid is only flowing, and when gas and liquid are flowing, now that liquid area available for that liquid flow is reduced and therefore velocity goes up. In addition, I need to drive those gas bubbles through the pipeline. So a lot more energy is required. Pressure drop when we have two phases flowing is more than that when single phase is flowing. So if there is a, let's say, a tank like this, liquid is draining and some liquid is coming in. When this liquid is draining, you get something like a vortex, right? It's like your kitchen sink vortex, right? You can do an experiment, just block the kitchen sink and then fill up water and then allow it to drain. You will see a nice vortex, and this vortex can be nicely visualized, and this is a vortex. And you see now that when this vortex breaks, these bubbles will go through this pipeline. So when bubbles go through this pipeline, pressure drop is more, and if it is a gravity driven line, then liquid will accumulate and it will maybe accumulate to a higher level so that the pressure drop can be met, so that it can force that liquid through this two-phase flow. So but once the liquid level rises, this vortexing action stops and then I get liquid only, and then liquid requires less pressure drop. So now I have a more head, liquid drives, liquid is driven out at high velocity, so this tank partly drains. So this alternately, tank fills and drains, tank fills and drains. So tank level sort of goes up and down, and then that causes disturbances in the flow. So we don't want that. So there are a couple of ways of doing that. One is to ensure that vortices don't form. There's something called as vortex breaker. You can search on the internet, or you can control the level by putting a control valve here. By putting a control valve here, you can put a level, you can measure the level. We saw how to measure the level, and then level can be controlled using this control valve. This control valve can open and close depending on whether the level is going down or level is going up. Or we can have a self-venting pipeline, means the liquid will go down like an annular flow, but gas, rather than going down causing two-phase flow here, gas will go upwards. Okay, and then gas can be disengaged. These are called as self-venting pipelines. And the way these are designed, there's something related to piping design, and they are designed based on a concept called as Froude number. So Froude number is velocity of the liquid divided by square root GD. Okay, and then you can relate this VL to the liquid flow rate, and there are guidelines that Froude number should be less than 1.6 H by D if your outlet is from the bottom, and if your outlet is from side, Froude number should be less than 1.4 HD raised to 0.5. If you want a self-venting pipeline, means gas has to go up, then Froude number has to be less than 0.3. So we will see the rationale behind all these as we go along, but these are very important when it comes to piping design. So those of you who are going into detail engineering companies, when they design pipelines, these things become very important. Okay, coming back to our pressure drop. So these are important terms, but right now let's not worry about them just now. I will just very quickly take you through this formula. The movie is there with you, or the video is there with you. You can again study it at leisure. There's something called as Lockhart-Martinelli method. So what that does is, first of all, you calculate delta P by L through the pipeline, delta P for a unit length of a pipeline, if only liquid was flowing. You calculate delta P if only gas was flowing. And we define a parameter X, which is related to square root delta P by delta L for liquid divided by delta P by delta L for gas. And then we call something called as a pressure drop multiplier. We relate that to the value X, so phi L square and phi G square, and we measure the two-phase pressure drop, or we can calculate the two-phase pressure drop based on this phi L square and only if liquid was flowing. So this is a homogeneous single phase pressure drop for liquid, homogeneous single phase pressure drop for gas. Use this formulae, and the use of this formulae are demonstrated here. So imagine that there is a pipe diameter 1 inch, schedule 40. So diameter is 26.6 millimeters. Total mass flow rate is, say, 750 kg per hour. So 0.2 kg is 0.21 kg per second. Gas fraction is 10% by weight, and that gas fraction is called as X. X is something called as quality. Okay. Yeah. So this quality is 0.1. So if I consider flow of, if I consider some properties, let's say rho g is 20 kg per meter cube, mu g is 7 into 10 raised to minus 6 pascal second, rho L is 800, mu L is 0.5 into 10 raised to minus 3, and surface tension is 0.008. And we calculate pressure drop using Lockhart-Martinelli method. What we need to do first is calculate the Reynolds number. So Reynolds number can be calculated based on the liquid flow only. Liquid flow would be this multiplied by the fraction of liquid. So 750 into 0.9. Okay, that's m dot L is slightly different. M dot L is here. M dot L is mass flow rate divided by cross sectional area, or mass flux. Okay. So D into mass flux. That's why that rho is not there. Rho into V liquid is this. Okay. So you know the mass flow rate 750 kg per hour for 0.21 kg per second. Gas fraction is 0.1, so that means liquid fraction is 0.9. So 0.21 multiplied by 0.9 will tell you the liquid mass flow rate divided by cross sectional area. That will give you the liquid mass flux. You just make sure that you get this number. So Reynolds number we can calculate, friction factor we can calculate, and then delta P by L for the liquid only we can calculate. Same way, mass flow rate of gas we know, 0.21 multiplied by 0.1 divided by the cross sectional area, that will give you the gas mass flux. Reynolds number we can calculate, friction factor we can calculate, delta B by L for the gas we know. Now go back to our formula. We can define this ratio 73.9 divided by 22 is here. 73 by 22. That will give you x square. So you can calculate x from there. X square would be 73.9 divided by 22. And x would be 1.83. So the two-phase multiplier we can calculate. Phi L square will be 12.2. Phi G square would be 40.96. So now the two-phase pressure drop would be phi L square multiplied by, for liquid, what is there for liquid? So 12.2 multiplied by 73.9. So 12.2 multiplied by 73.9, 902. Or we can do it from gas, 40.96 multiplied by 22. 40.96 multiplied by 22, we'll still get 902. So that's how we can calculate the two-phase pressure drop when we are talking about flow of gas and liquid in a pipeline. And these things become very important, especially in a case where we are talking about steam flowing. So steam partly condenses, we have a water and steam mixture going through the pipeline, or crude oil pipelines, natural gas pipelines. When crude oil pipeline is there, so crude oil is being pumped. Crude oil is liquid, but there is some dissolved gas in that. So when it comes out inside the earth, it is at a higher pressure. When it comes out, part of the gas comes out from the dissolved state into the vapor state, and so what you have transported in the pipeline is a crude oil liquid and a small amount of gas that goes through the pipeline. So the gas is typically methane, hydrogen, ethane. Those are lower molecular weight compounds. And this two-phase flow is therefore very important. We need to estimate pressure drop in that two-phase flow. Natural gas. So when natural gas is taken out from Earth, some of the liquid condenses, and then you have a liquid and gas two-phase flow. So two-phase flow is very important in industry, very important for pipelines when they are being transported, when you're transporting gas and liquid through the pipeline. Sometimes due to pressure, gas is generated, or gas, say for example, if I'm trying to pump crude oil, let's say pressure at where I'm pumping the crude oil is very large, so I have nice liquid crude oil going through. But as we go along the pipeline, pressure reduces, pressure drops, so the gas solubility reduces, and we get the dissolved gas comes into the vapor state. So as we go along, as pressure drops in a pipeline, more and more gas is generated, and the relative ratio of the gas and liquid coming out becomes larger and larger. Right? So therefore, the two-phase flow, this pipe has to be designed, the pumping system has to be designed properly to account for the extra pressure drop because of the gas. Another example is when we are talking about same thing when we talk about natural gas, or another example is when we are talking about steam flow. So steam is flowing, but there is a heat loss to surroundings, so part of the steam condenses, and we have water drops going along with this steam, and then the water drops going along with this steam causes extra pressure drop, and we need to take that into account for calculating properly the pipe sizes. Has to be sizes and the layouts has to be taken into account for all this to account for this two-phase flow. So this is a very important part, and although in your undergraduate course you may not use it very often, but this is a very important consideration, the two-phase flow. That you can do an experiment, we will have an experiment where you can actually see the flow of two phases in the pipeline, and you can measure and you can verify your answers with the two-phase flow pipeline, or the Lockhart-Martinelli method. Okay, so that brings us to the third part of our course related to Bernoulli equation. This material for your reading you can find in Fluid Mechanics book, Frank White, 7th edition. We have done chapter 6 except section 6.5. Okay, and related to things like Wears and V-notch, that is in chapter 10, section 10.7. Section 6.5 is related to turbulence modeling and so on. Let's not do that. We will do that as we go along. We have a different place for that in the course, and you can solve these problems from the book. So these are the minimum problems you should solve. Again, the book has more than 150, close to 160, 170 problems at the end of chapter 6. You can solve these. I'm only suggesting you solve 6, 7 of them, and once you solve these problems, all these concepts will be clear, and it will help you to sort of put all the things that we have done into proper perspective. So that brings us to the end of third part of the course related to Bernoulli equation.